Hello everyone, I welcome you all in today's lecture. In the previous lecture on connections in steel structures, we had actually missed out the tension connection and the combined shear and tension connection. As you can see in the figure, a hanger connection is shown. In this connection, the load transmission is by pure tension in the bolts, because the direction of the load and direction of the axis of the bolts is in the same direction. So these bolts are subjected to direct tension. While as in figure B, we have a connection shown and the bolts are in this case are subjected to both tension and shear, because the direction of the force is inclined. So we will have two components of the force, that is horizontal component in this direction, and we will have a vertical component of the force in the vertical direction. So due to this horizontal component of the force, there will be tension in the bolts, whereas due to vertical component of the force, we will have shear in the bolts. Now we have types of bolt joints, that mainly lap joint and butt joint. Figure shows the three-dimensional view of a lap joint. We call it as single bolted lap joint because we have provided a single layer of bolts. We call it as single bolted lap joint. In lap joint, one plate is placed above the other and these are joined by the connectors, and in this case we have connected them by bolts, one line of bolts, so we call it a single bolted lap joint. This is the plan of this bolt joint, and this is the longitudinal section of the bolt joint. That is, if we cut a section along the length of the member or along the length of the joint, we will have a longitudinal section of the joint as shown in figure. Similarly, we have a butt joint. This is called single cover butt joint because the two plates are abutting each other and these have been connected by a single plate, that is called cover plate. So this joint we call single cover single bolted butt joint because we have provided one layer of or one line of bolts in one plate and one line of bolts in another plate. So we call it as single bolted single cover butt joint. And if we place two rows or three rows of the bolts on each plate, we call it accordingly single cover double bolted butt joint and single cover triple bolted butt joint. We have a double cover single bolted butt joint, that is, the two plates are abutting each other and these have been connected by two cover plates, one on above the plates and one below the plates, and these have been connected by one row of plates on each plate, so we call it as double cover single bolted butt joint. This is the plan of the double cover single bolted butt joint, and this is the longitudinal section of the double cover single bolted butt joint. That is, if we cut a section along this direction, we will be able to see two plates that are joined by bolts. There's one line of bolts and we have another line of bolts. Similarly, we have a single cover double bolted butt joint. As you can see, we have two plates abutting each other and we have connected them by a plate and we have placed two rows of bolts in each plate, so we call it as single cover double bolted butt joint. Now as you can see, in the case of lap joint, the bolts are in single shear. That is, there is only one plane of shear failure at the interface between the plates. So due to this load P, there will be bearing of P on the bolt on the upper side of the plate, and similarly due to this load there will be bearing of P on this side of the plate, because the load gets actually transferred from the plate to the bolt. So the section at this location will be subjected to shear force P. So the bolt in case of lap joints is in single shear. That is, the failure plane will be at the interface of the two plates. Whereas in case of butt joints, double cover butt joints, we will have double shear. As you can see, the load P gets transferred to the upper cover plate and the lower cover plate as P by 2 and P by 2. So the bearing on the bolt at this location will be P by 2, and the bearing on the lower portion of the bolt will be equal to P by 2. So bearing on the lower portion of the bolt is P by 2 and the bearing on the upper portion of the bolt is P by 2. So we will have a shear of P by 2 developed at this interface and at this interface. That is, at this interface we will have shear force developed as P by 2, and at this interface we will have shear force developed as P by 2. So there are two planes of shear failure, or there is tendency of the bolt to shear at these two locations. So we call it as double shear. Now let us discuss the grade of bolt. Bolts are grouped under different grades or property clauses depending upon their strength. Bolts are available in grades 4.6, 8.8, 10.9 and 12.9. The majority of structural connections are made using 8.8 grade, with 4.6 grade generally being reserved for secondary connections, for example purlin cleats or lacings in case of trusses or truss members. As far as the grades of the bolts are concerned, the first number denotes the 1/10 of the minimum ultimate tensile stress in kilograms per square millimeter, while the product of the two numbers gives the minimum yield stress in kilograms per millimeter square. For example, we have a grade of 8.8 grade. For this grade, the minimum ultimate tensile stress is equal to, because this is 1/10 of the ultimate tensile strength, so we will get it as 10 multiplied by 8, so that will be 80 kg per millimeter square. which would be approximately equal to 785 Newton per millimeter square. And the minimum yield stress for this grade of the bolt will be equal to the product of the two numbers, that is 8 multiplied by 8, that will be equal to 64 kg per millimeter square, and that will be equal to 628 Newton per millimeter square. Now we have different types of bolts available for connecting structural steel members. We have black bolts, turned and fitted bolts. We have high strength friction grip bolts. Black bolts are also called ordinary or unfinished bolts. These bolts are made of mild steel and are usually of grade 4.6. These are used for light structures subjected to static loads and for secondary members such as purlins, bracings, and for roof trusses. The nuts on bolts are tightened with wrenches, producing very little tension in the bolts. Therefore, no clamping force is induced on the section being joined. These bolts are available from 5 mm to 36 mm in diameter and are designated as M5 to M36. Then we have turned and fitted bolts. These bolts have uniform shanks and are inserted in close tolerance drilled holes and made snug tight by box spanners. Snug tight is defined as the tightness that exists when all the pliers or members in a joint are in firm contact with each other or with one another. The diameter of the bolt hole is about 1.5 times to 2 mm larger than the bolt diameter for ease of fitting. As you can see in the figure, we have an unfinished bolt or black bolt or ordinary bolt connecting two plates. These bolts fit loosely and there is no clamping action on the plates being joined. So as you can see, there is a clearance on both the sides, that is these bolts are loosely fit. When the load is applied on these plates, there is a shearing action on the plates resulting in the slipping of the plates until the shank of the bolt comes in contact with the edges of the hole. As you can see in the figure, the shank is in contact with the plate. Similarly here, the shank is in contact with the plate because due to this tensile load, there is a displacement of this much, and so this gets in contact, the upper plate is in contact with the shaft or shank of the bolt. Because the direction of the load is in this direction, so the bolt gets displaced in this direction and it actually meets the plate on the other side. So there is the plate is bearing on the bolt here and the plate is bearing on the bolt here. The load is thus transmitted by bearing on the bolt and shear in its shank. So there is bearing on the bolt as well as the development of shear in its shank. The shank of the bolt bears against the edge of the plate, resulting in high local stresses and consequent local yielding of the material. Hence, such a bolt is not desirable if the value of the load is very high. Whereas, in the case of turned and fitted bolts, when the plates are subject to load, since the bolt fits tightly in the drilled holes of the plates, no slip would occur because these are tightly placed or tightly fitted in the holes. So there is not possibility of any slip. The load for such a case is directly transferred by bearing and shear in the bolt. So there is direct load transmission by bearing and shear in the bolt. So no localized bearing stresses are produced. Therefore, higher values of load can be permitted in the case of turned and fitted bolts. Normally, for ordinary bolted joints, the force is transferred through the interlocking and bearing of the bolts. However, for high strength bolted joints, this transfer of force is accomplished through the friction between the interfaces formed between the load carrying elements joined together. This friction is developed by applying a load normal to the joint by actually tightening those bolts to proof load. That is why these bolts are also called as friction type bolts. So high strength friction grip bolts provide extremely efficient connections and perform well under fluctuating and fatigue load conditions, whereas the turned or ordinary bolts are not fit for fluctuating loads or fatigue load conditions. So when high tensile strength bolts are fully tensioned, they clamp the parts being connected tightly together. The result is a considerable resistance to slip on the connected surface. As you can see in the figure, is shown a high strength friction grip bolt connection. As you can see, the pretension in the bolt causes the clamping forces between the plates even before the application of the load. When the external load is applied, the tendency of the two plates to slip against each other or against one another is resisted by the friction between the plates. So the frictional resistance developed at the interface is equal to the coefficient of friction, that is mu, multiplied by the normal clamping force between the plates. So until the externally applied load exceeds this frictional resistance, that is mu f, the relative slip between the plates is prevented. So the load transfer is actually by the frictional resistance. The high strength friction grip bolts or bolted connections are designed such that under service loads, the force coming on the structure or coming on the joint does not exceed the frictional resistance, so that the relative slip between the plates is avoided during the service life. But when the external force exceeds the frictional resistance, that is mu times F, the plates slip until the bolts come in contact with the plate and they start bearing against the sides of the hole. So if the load coming on the plates is more than the frictional resistance, there will be displacement of the plate, so there will be direct bearing of the plate on the bolt. Similarly, in this case, there will be displacement of the plate in this direction, so there will be direct bearing of the plate on the bolt. So there will be direct contact between the two surfaces, that is bolt surface and the plate surface. Beyond this point, the external force is resisted by the combined action of frictional resistance and the bearing resistance. So once the load is beyond the frictional resistance limit, the external force will be resisted by combined action of friction and bearing. So the tension in the bolts ensures that no slip takes place under working conditions, and so the load transmission from plate to the bolt is through friction and not by bearing. High strength friction grip bolts are made from alloy steels, which are quenched and tempered with grades from 8.8 to 10.9. The most common are the so-called general grades, that's 8.8, and have medium carbon content, which makes them less ductile. The 10.9 grade has a much higher tensile strength but lower ductility. Now we have in figure a lap joint. There is two plates are joined by bolts in three lines. This is called chain bolting, and the distance from center to center of the bolt, that is this distance, along the direction of the load or along the direction of the stress is called pitch. So actually pitch is the center to center distance between two consecutive bolts or rivets in the direction of the stress. When the bolts are placed staggered, the pitch is called staggered pitch. Similarly, the distance, that is center to center distance between the consecutive bolts measured along the width of the plate, or center to center distance measured perpendicular to the direction of the load or direction of the stress, is called gauge. Similarly, the distance at right angles to the direction of stress, that is this distance, from the center of the bolt to the adjacent edge of the member is called end distance. whereas the distance in the direction of stress, that is this distance from the center of the hole or from the center of the bolt to the end of the element, is called the end distance. This distance is called lap length or lap distance. That is the overlapping portion of the two pallets is called the lap length or lap distance. So that is all in today's lecture. Thank you.